So today we have the pleasure of having Shane Henderson from Cornell, who will give us a tutorial and perspective from Monte Carlo simulation and optimization.
Okay, thank you for coming, and thank you to Simri for the support and to Lyndon Roberts for serving as my host. I've been learning quite a bit from him and enjoying the visit. So great fun. I was trying to show you a little demo of simulation optimization models. So what I would like to discuss is simulation optimization. And when I use the term simulation, that's often used in applied math in different ways. So some people view the term simulation as solving PDEs. Some people will use it for live simulations where you're actually like medical exercises, where you have people that pretend to be casualties and so forth. Those are not the ways in which I'm using this term. I'm using this term in the sense of Monte Carlo, meaning that I have some computational framework that involves generating random numbers, and those random numbers play an integral role within the calculations. So I want to explain this through some examples in a second, and then I want to sort of point out that this area is young. It has some connections with training and machine learning, but there are sort of fundamental differences in some of the aspects that show up. So this is the way that I want to, the material that I want to cover. I want to go through a few principles that are used in this area that are very important for designing algorithms for solving these problems. I want to show you that something called a sample path function, which is the thing that we can compute, can be a strange object. And they can be beautiful and tractable. They can also be ugly. And so I want to explain why that happens and show you what those structures look like. I want to talk a little bit about how one can develop analytical results for convergence times, those kinds of mathematical results. And then if there's time, I want to show you some work that we've been doing on building out test suites of problems and diagnostics for these algorithms. And probably won't get to those. So we'll see how we get on. So maybe I'll just move on. So the problem that I am thinking about is the following. I want to minimize over some set of decision variables X. You can think of that as a vector in Rn. I want to minimize some real valued function. So that's this guy here, but it's actually expressed as an expectation. So the true nature of this function that I want to minimize is an expected value of something else. And it's the something else that I can actually compute in the computer. So I can compute this f of x comma c. So what is going on here? So I have some decision variable x or decision vector x. Think of that as finite dimensional. Then I have this c, which is this random thing. You shouldn't think of that as just a real random variable. It's could be very, very complex. It's some random structure that we can generate in the computer using Monte Carlo. And then we have the simulation logic, which is this function here. This guy over here is representing all the complexity of the simulation model that is doing all the logical calculations to take your decision vector x and your random information, combining those to give you some sort of output. Think of that as real valued. And then I'm taking the expectation of that, and I want to minimize that. Okay, so that's kind of the framework. I'll give you some examples on the next slide of this framework. So the domain D, capital D that you see there, I don't want to get into it. It's just some straightforward to work with domain. Think of it as like box constraints, so lower and upper bounds on all of your decision variables, for example. Importantly, the C here, the random element, its distribution does not depend on my decisions. So, for example, if you're working with portfolio optimization, so you're trying to decide which stocks to buy and so forth, then the distribution of your portfolio is going to depend on which stocks you buy. And we would figure out a way the term is push out. We would remove the dependence on this decision variable X for that portfolio. There's ways to do that. I'm just not going to go into it. So X is something we can adjust. It's got nothing to do with XC. And if you're familiar with Monte Carlo, you know that Monte Carlo simulations are built from the ground up using uniform random numbers. So if all else fails, just think of the XC as being all of the uniform random numbers that go into the calculation. And then what I've written down here is mathematically consistent. Okay, so because we can't exactly compute this expectation, we're going to have to do something else. So we'll use sampling. So we'll sample an IID sample here, C1 through Cn, and we'll just take the sample average of the right-hand side and use that to approximate the expected value. Okay, so at any given X, I can sample to get an approximation of the right-hand side, and I can adjust the accuracy of that approximation by increasing the sample size. Okay, so here's some examples where this framework might show up. So we're going to see the news vendor problem. This is a very simple problem. So the idea is I'm just choosing how many newspapers to buy as a person who's going to go out and sell newspapers. So I am buying physical newspapers. This is back in the dark ages. And I'm going to have to buy them in advance. They cost a certain amount to me to buy, and then there's a single item purchase, but then my sales is going to be the minimum of whatever I purchased and the true demand. Okay, the true demand is random. Therefore, I'm making this decision before I see that randomness, and so I have one of these optimization problems. That problem turns out to be a toy problem that we can solve easily. It's very straightforward, but it's a good example problem that I want to show you that enables us to develop some insight. The second problem is a little bit closer to reality. And so this second problem is where you're trying to choose the locations for your ambulance bases in a city. And so you may or may not be coming at this fresh, right? You may only be sort of modifying the locations of one or two bases. But in general, sometimes with blue sky kind of calculations, meaning all bets are off, you're considering all possible locations through the city. And the question is, where should those ambulance base locations be so that you get good on-time performance? And so in those situations, the output of the simulation could be something like the mean response time to calls. It's usually not the mean response time, it's usually something else, but that's good enough for us. Okay, so that's a second problem that I was that I've used as motivation, and it's the one that I was sort of hoping to show you on my other machine, but you know, no joy there. So the third example I want to mention is one that I worked on extensively with New York City. So there we have a bunch of stations throughout the city, something like 1,000 bike stations, and we're trying to determine how many racks to place at each one of those 1,000 stations, so as to ensure that people who go to pick up bikes can find one, and people who go to return a bike can find an empty spot. And it turns out this is actually a very important problem for Citi Bike in New York City, and in fact, in all bike sharing programs that use station-based systems. And you may think that station-based is so last century, right? Like we should just drop off bikes wherever we like. And that's true in some parts of the city, but certainly not in the really busy parts. So if you're near Grand Central, you've probably seen that is insanely busy. And around that area, you do have to have racks to put bikes back. Otherwise, it just becomes chaos because there are several hundred bikes that are sort of floating around in that area, huge amounts of traffic. And then the final example I want to mention is something that we worked heavily on at Cornell. We ended up managing to keep the university open throughout the pandemic, except for a few months in sort of March through May of 2020. We were able to reopen later that semester, later that year. And the way we did that was through extensive testing, surveillance testing, and then isolating positives. And for that, there's an interesting question, which is how frequently should you test people in different groups. So graduate students, undergraduates, and so on. Should we test them twice a week, once a week, some other frequency? And it turns out that that can be formulated as one of these simulation optimization problems, where the simulation is a representation of one semester's worth of activity, and you're looking at maybe risk-weighted infections as your output. Okay, so these are all examples of these simulation optimization problems. So the difficulties in this situation are sort of several. So you can view this as a black box optimization problem where you just have some evaluator that evaluates your function, and then you do your best to sort of search across that space. And sure, you can do that, and that'll probably be fine in moderate dimensional problems. You can do something reasonable there. But for the kinds of problems that I would like to tackle, this is usually hopeless. So we're going to have to look for some more structure somewhere. And there's a few things that are going to help us out. So first of all, we can characterize the error in our approximations at any single point pretty easily. So for example, the central limit theorem is going to tell us, right? So if I want to estimate f of x, we know that we can approximate that by the sample average of these guys here, right? So I just generate sort of in my semester problem with COVID, I would generate n semesters, and I would average the responses from each one of those, and that would be a Monte Carlo estimator of this mean. And that's just a sample average. So if I scale that up by square root of n, and if I have finite variance, which I invariably do in my problems, this will converge to sigma times a normal 0, 1. It's just the standard central limit theorem, where sigma is the variance of one replication, a standard deviation of one replication. Okay, so that tells me that my estimator has an error that's of order 1 over square root of n, because I just divide both sides in some sense by square root of n. But it's stochastic order 1 over square root of n, because the right-hand side here is random. And therefore, I have to put a sort of a big O sub p of 1 over square root of n. And the difference is really just, if you're familiar with this topic, this is basically tightness in the language of probability. But in the language of just sort of staring at it and trying to figure out what's going on, there's a random variable divided by square root of n on the right-hand side. Okay, so that's kind of the intuitive way to think about this. So this tells me that my estimates are going to converge really slowly. 1 over root n, it's terrible, right? We'd love to have something like 1 over n squared or something like quadrature rules and things like that, but we don't have it here. So that means that the statistical noise in the estimates can overwhelm the true difference in function values. So I'm comparing two solutions, two proposals, x1 and x2, and I want to know which one's better. So I simulated x1, I simulated x2, and I see how they're ordered. But the error in both locations is of order 1 over square root of n. So that's big, and that means that it's super hard to tell which one is better. And so that's going to be a problem if you're doing optimization. So that's an issue. That you could, during the course of your search, you could visit the truly optimal solution, and you just wouldn't know that. You would just blow right past because you've got this error in the estimates. That's an issue. You can never be certain when you've got a solution whether it's going to be optimal or not. All you know is that it looks pretty good. Yep. Yeah.
Yes.
Yep. Quasi Monte Carlo. Sure. One could extrapolate to view it that way. Yeah. So quasi Monte Carlo, typically the convergence rate is something like log of n to the power of some quantity divided by n. And the Monte Carlo rates are like 1 over square root of n. So the quasi Monte Carlo on paper looks like it's faster. And that certainly has been observed when you have problems with low relative dimension. You probably know all these terms. But if you're in a problem in high dimension where it actually exhibits high dimensionality, intrinsic dimensionality, then quasi Monte Carlo can be horrible. And Monte Carlo is far better. So it depends on the situation. Certainly, if you're even in more structured situations, absolutely, I love quadrature. So I would always go, if I can apply quadrature rules or some other faster converging method in general situations, great. But in many of the problems that I'm looking at, those methods don't apply either because the dimension is not fixed, sort of somewhat random. That happens in the Monte Carlo kind of the ambulance example for yeah. I mean, no. So I'm absolutely a convert to using the right numerical schemes for the integration here to compute the expected value. I guess what I'd like to do is sort of just say sometimes those methods don't work, and within that structure. Thanks, Marcus. Great. Okay, so oh, I'm sorry. Yeah, absolutely. Are you using any structure? So far not, but I'll try to impose that in a bit. Yeah, absolutely. So, at least within the framework that I'm posing here, we can't expect super accurate solutions. It's just not going to happen. And so that's a bit of a downer. But what can we do? And so the thing that's going to help us a little bit, but I'm not going to emphasize today, is that these problems are embarrassingly parallel. Parallel means you can implement it on a parallel computer. Embarrassingly parallel means basically it's super easy to do that. One replication per computer, you're good. So that certainly is in our back pocket, but I'm not going to talk about that any further today. So you should just assume implicitly that that's present, but we're not going to emphasize it. So these problems, if I just pose it the way I have so far, yeah, it's pretty hopeless. So I'm going to have to impose some kind of structure, and that's actually a bit of a theme throughout. Okay, so here's one principle that is going to help us a little bit. So I've got two proposed solutions, x1 and x2, and I want to know which one of those two solutions is the better solution. So one thing that you might think about doing would be to simulate at both x1 and x2 and compute confidence intervals around each one of those two solutions. And then when those confidence intervals don't overlap, you'll declare one to be the winner, right? Because as you increase the run length, those confidence intervals get narrower at the rate of 1 over square root of n. And so we'll do that. Now, it turns out that's super conservative from the perspective of telling which one of these two solutions is the better one. It's you can typically get far more accurate comparisons with much shorter run lengths than that. And the reason is the large deviations behavior of what's happening. So think about the true function values being at these levels here. In order to get a mistake, in order to get the ordering wrong, your estimates have to be reversed in their ordering compared to the truth. That represents a large deviation of the means of those systems away from their true values. Once you get into large deviations, the convergence rates are far faster than 1 over square root of n. For light-tailed random variables, doesn't matter what that means really, typically the rates are exponential. It's like e to the negative n. And so what that means is that even though the confidence interval half-widths might be going down pretty slowly, here you see them coming down here, the probability that you get the ordering reversed, don't worry about the context here, it's just a sort of a stylistic example. The probability that you get the ordering reversed on these guys is going down super fast. So that means that the run lengths that you need to get the ordering right between two solutions can be quite small. Even though from the perspective of computing half-widths, those half-widths might still appear to be fairly large. And the reason that there's a difference, the reason there's this sort of incongruity here, is that the central limit theorem is an asymptotic result for moderate deviations. And when you're looking at this kind of situation, you're looking at some finite run length n which may not be in the asymptotic regime, and you're looking at large deviations. So you can be in a different situation. You're looking at the tails of random variables instead of the middle. And the central limit theorem is all about the middle. Large deviations is all about the tails. So there's a difference. And this means that basically you can have shorter run lengths and still get the orderings correct. A second thing that's in our favor is common random numbers. So the idea here is, again, I want to compare two solutions and see which one is the better. And in this left-hand panel, you see that I've computed a sample average for x1 and a sample average for x2. And I'm using different random numbers in those two situations. So here, I is running from 1 to n. Here, it's running from n plus 1 to 2n. So I want you to think that we've done independent replications for the first guy, separate independent replications for the second guy. So think about the ambulance problem for a second. I've simulated 100 days at the first proposed set of bases. The other one, I've simulated a completely different set of 100 days. That should bother you. maybe it's better to do what's called, a fair comparison. Use the same simulated sort of primitives in the two situations. That's the notion of common random numbers. So I use the same random variables in these two settings, and sorry, down here, I use the same random variables in the two settings. So it's kind of like I'm comparing apples with apples. And this is almost always the right thing to do. There's a couple of settings where you might actually make things worse for yourself, but I've never encountered them in practice. Basically, as long as you have positive correlation between these outcomes and these two events, it's going to be the right thing to do. So you're intuitively, you're doing a fair comparison. You're just running the same random variables in each situation. But from a conceptual perspective, it's all about coupling and the joint distribution between these two objects. And that turns out to have a huge difference in practice. So I'll come back to that, in fact, right now. So perhaps you've heard of empirical risk minimization in machine learning, or perhaps you've come across sample average approximation, which is another principle. They're basically the same thing. So here's the idea. So we're going to generate a sample of n of these random objects. Think of that as n sets of random elements Xi. And we're going to fix it. It's no longer, in our mind, random, right? It's fixed. And then what we're going to do is we're going to try to optimize that sample average function, which now, conditional on the sample I just generated, is deterministic. So think of it as sort of like generating and fixing all the random stuff you're going to see in n instances, and then just living with those n instances. Okay, so that's the idea behind sample average approximation. Here we choose the x that minimizes that average of n random elements. And now we can use deterministic optimization algorithms on that problem. That's a huge advantage of this approach. And you may have heard of empirical risk minimization. Those objective functions typically look like this down the bottom. And I'm changing the notation on you just a little bit. Previously, x was my decision variable, but down here, think of beta as your decision variable. And I use beta because it's sort of reminiscent of things like regression, right? Those are your variables. And then you have input data and outputs, and you're trying to minimize the loss here associated with a particular set of betas. And then here we're doing the empirical loss over all n learning objects. And so in machine learning, there's all kinds of ideas like when you're minimizing this thing, just pick one of those n instances of data at random and do something with that. That's very similar to the notion that I'm using of randomly picking an Xi. So there's strong parallels between these different areas, and much for the people in the simulation community to learn from the ML community. And, hopefully the other way around, but we'll see, So anyway, so this notion of sample average approximation is fix the sample and then estimate the function at any given point x with this empirical average. And now it becomes important what those functions look like. Are they tractable? Are they nice? Are they amenable to optimization, or are they a mess? And that's something that I want to explore just a little bit more and give you some intuition for that. There's another principle that we'll look at just before I get to showing you those sample functions, and that's this notion of optimization bias. So here's the idea. You fix your sample of n objects, right? These n X's. Now you optimize, fixing that sample, and you get this guy. And let me just explain what that is. Xn star is the optimizer for that sample function, right? And then Fn of Xn star, that's me plugging that estimated solution back into the estimated function and seeing what its value is. Okay, that turns out to be biased low for minimization problems. It lies below the true optimal value that you're trying to seek. And the effect can be quite large depending on the distributions that are involved. So let me sort of explain that in a very stylized setting, and then you'll sort of see it's sort of obvious, right? So here's kind of the idea. Suppose that my function is incredibly boring. It's a constant function. So it doesn't matter where you choose your x, it's all optimal, right? But now whenever I sample at any fixed point, I'm going to get something that is sort of distributed around that point, right, as my objective function value. And we know it's roughly normally distributed by the central limit theorem. So I'm going to get some sort of sample from a normal distribution here. And then I go somewhere else, and I'll get something else that's sort of normally distributed. And in this process of minimizing the sample function, I'm just going to pick whichever of these points is the lowest. So maybe that point happens to be over here, and the true objective function, the objective function value that I observe is down here. Now we know the truth is on that horizontal line, but by focusing on the lowest of these points, we're immediately biasing ourselves low. And so if we just plug in the estimated optimizer into the estimated function, we're going to screw up, and we're going to think things are better than they really are. So you have to, once you've identified your solution, what's the fix, you just do another set of independent replications at that point, and that's going to then be unbiased around the true value. So that'll sort of address this to some extent. So the way that this is expressed, using probability is like this. The expectation of that value is below the true value, and the effect can be big. So you've got to be careful of this. And the proof is like 2 lines, so I won't bore you with that. But it turns out actually there's something very interesting that happens with that sequence of function values. If you view it as a sequence in N, it turns out while it's biased low, as you increase your sample size, this bias sort of dissipates. That should be intuitive, and the proof is actually kind of beautiful. So I just want to show you quickly how that proof goes. Okay, so I'm going to show that the expected value of this value with N plus 1 samples is smaller than the value it's bigger than the value with N samples. Okay, so it's going up. And remember, it's biased low, so because it's an increasing sequence, it'll converge and blah, 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 right? It's all good stuff. So that expectation is just the expectation of this. I've just re-expressed my sample average over all N plus 1 terms. And now I'm doing something sort of interesting here. I'm actually just computing that average of N plus 1 terms, but in a sort of a redundant manner. So what I've done is in here, I'm averaging over N terms. I've just dropped one of them, dropping each one in turn, and then I'm averaging over the ones that I'm dropping. So this is just, these two things are just sort of going from here to here is just a redundant way of doing the averaging. But now I do something interesting. Now before I was minimizing, I had to pick one X for this optimization problem. Now I can customize my X depending on whichever one I've dropped. And because I can customize my X for whichever one I've dropped, I'm going to get an improved lower bound. It's going to go lower. And if you look at this is equal in distribution to the original problem with N samples, because I've still got N samples and I'm averaging them. So this part looks just the same as the Fn sort of part. So when I'm minimizing this guy, this has Fn of xn as it's sort of equivalent to this. So take expectations of that, I get something here. And now on the outside, I'm just averaging in constant. So it's quite interesting that there's this monotonicity in great generality of this sort of bias down below. So it's kind of fun. It's interesting. It helps cement some of the ideas. So that's why I'm showing you this. So let's move on to those sample functions. The reason that they're important for us to understand is that that in turn drives how we design algorithms. So if these algorithms have, if these problems have structure, we can exploit that. So that's your comment. And so sometimes these sample functions are super nice. So here's that newsvendor example again. So we're buying at cost C, each newspaper. We're selling them at some price R that's bigger. And so the demand is random. And so we want to maximize expected profit, but I'm going to flip that over to minimizing the negative of negative profit or something. So here's the cost of buying. Here's the revenue that I earn. This is representing the minimum. And so that's my sample function for one realization. And then when I average that over multiple realizations, so here I have 3 realizations, I get a function which looks like this. It's piecewise linear. And it's piecewise linear convex. And therefore, it's super easy to optimize this function. You don't actually need to do this. You can just go straight to a quantile of the demand distribution. That's the optimal solution. But you can write this thing down. It's piecewise linear, and therefore it's super easy to solve. It's convex, great for minimization problems. So everything is good. Okay. But sometimes, in fact, usually I would claim that for the problems that I think about, like the ambulance problem or the testing frequencies problem and so on, my sample functions are horrible. So here's another trivial example where the structure is just, it's awful. So here, what's happening? Totally contrived example, but it brings out the right idea. So passengers are arriving to this bus terminal as according to a Poisson process with a certain rate. And so that's sort of the most beautiful arrival process shows up everywhere. So we've got one bus that's departing at time 1, and we're trying to schedule the time for the other bus. When should the other bus leave? Just one other bus. And the goal is to sort of minimize passenger waiting times, right? And I'm ignoring capacity issues and all that kind of stuff. These are infinite capacity buses. Gotta love those ones. I wish that Sydney had some of those, actually. That 423 bus that heads down here, it gets really packed. Anyway, so this is the setup, right? And just by symmetry, right? Purely symmetry. Clearly, the answer is you would schedule the other bus at time 1/2. And indeed, that is the optimal solution. You can write it down in a few lines. But let's think about what would happen if you tried to throw this at a simulation optimization algorithm. So what would the simulation optimization algorithm do? It would generate customer arrival times, passenger arrival times over this interval. And it would do that multiple times. And it would just compute the empirical average waiting time. And it turns out that that sample function looks like this. Okay, what's going on? Just think about on the horizontal axis here, I'm moving the time of the bus. Actually, I'll just do it over here so people online can see. So I'm moving the time of the bus departure here. When the bus that I'm scheduling is at time 0, everybody has to wait the full 1 time unit till the last bus. But as I move this guy across, eventually I'm going to have the bus depart just after somebody's arrived. At that time, that customer ends up waiting substantially less time. There's a drop, and it's a discontinuity. And then that customer then has to wait longer and longer as the bus departure time gets further delayed until the next passenger time of arrival. And again, you get this kind of drop. So you see these kind of precipitous drops here throughout, and then sort of increasing between these curves. So this function is not convex. It's not bowl-shaped. The true function is actually just a parabola. It's just really ugly. And remember that with these optimization problems, they just have local information. They're just sitting at one point here. So they only see maybe the local slope and the value. But we want to optimize this thing. That's the problem. Okay. So what goes, what is it about this strange example that is sort of so interesting or whatever? Well, it is very artificial, but it's quite representative of what happens in a lot of problems. So let me just say a couple more things that are interesting about this, this problem. So here's that sample path function again. You get discontinuities or jumps of size 1 minus ti. So what is this? So most passengers are having to wait for the full 1 minus ti time until their bus, because they're arriving at time ti, they leave at time 1. When that bus first comes immediately past their arrival time, they drop to 0. So there's a jump of that size for that passenger in their waiting time. When I'm averaging this over n replications, the jumps are of order 1 minus ti over n. That's a random variable over n. So the size of the jumps in these sample functions are of stochastic order 1 over n. Moreover, as you increase your samples size here, the locations of arrival times of these customers, which are uniformly distributed in this interval through properties of Poisson random processes, those are uniform, and therefore those are becoming dense in the domain that we're optimizing over. So these discontinuities are of size 1 over n. There are on the order of n of them, both things stochastic. And so as n increases, you have dense jumps of very, very small size and very poor structure locally. But overall, you're going to start tracing out that parabola. So this is an interesting kind of structure for these sample path functions. And unfortunately, this kind of structure is the norm. It's not the exception for the problems that I face. So here's another example. Again, sometimes the function is nice. So here I've got stylized version of my ambulance problem. I was going to show you a real simulation model for Melbourne, but can't do it. But basically here, you've got calls showing up in some city that's represented by the square here. I've got ambulances that sort of travel, in this stylized model, straight lines to the call. And then they spend some time at the scene, and then they don't even transport patients to hospitals. They just come straight back to the base. And they can be diverted off to the next call if the next call comes in early enough. Okay, so that's the model. If you have only one ambulance and you're trying to optimize its positioning, this is kind of like a center of mass problem. It's very easy to solve. It's a convex optimization problem. Everything is beautiful. Okay, great. So as long as my city only requires one ambulance, I'm in good shape. What happens if I require two ambulances? Well, everything blows up. So again, I've got that same setup as before, but now I've got two ambulances, and I'm going to position one ambulance base here, just for demonstration purposes. That's fixed. And then I'm moving the other one around this unit square. Okay, so what you're seeing over here on the left-hand side is a contour plot of one of these sample functions. And you can see that it does have a sort of an overall bowl shape, but there's all kinds of local areas that are messed up, right? And that's being created by these discontinuities. And on the right-hand side, I'm showing you a diagonal slice, the sort of this diagonal through here of that function. And what you can see is this kind of crazy stuff here, right? That's again, those discontinuities. And you've got the same kind of thing here, but it seems less pronounced. And then in the middle, it looks great. But actually, if you zoom in, it's the same issue. Okay, so is this, what's going on here? Well, why is this function not nice? Because it turns out there's a principle that you can immediately, with intuition, just tell immediately for your problems, whether they're going to have nice structure like the news vendor or ugly structure like the bus. And that principle is the following. Do you expect your sample path functions to be continuous and piecewise differentiable? And if that's true, then you're good. You need a little bit more. You need some uniform integrability. If you know some probability, you know what that is. If you don't worry about it. It's not that big a deal. It's basically a regularity condition. But here's what's going on. So I have my sort of square of my city here, and I've got this one base up here at 15, 15. This is running from 0 to 20. And what's happening? Well, suppose that I've got a call that shows up here. Okay, so somebody has just called in, and I have my my other base is sort of way over here somewhere. So that's my other base. So in this situation, when both ambulances at those locations are available, then this call is answered by this ambulance here. Okay, so everything should be fine. But as I move this guy along, remember I'm varying the locations of the bases. At some point, I might get closer to that call than the other ambulance, in which case that call will be picked up by me instead, by this other ambulance base. For that call, it experiences the same response time regardless. But for the downstream calls that might come in later, everything is scrambled up. So this creates discontinuities in the sample path functions, and those are the bad guys. Right? So that's why these sample path functions have this strange behavior. So if you have a problem for which the sample path functions are continuous and piecewise differentiable with just a tiny bit of regularity, uniform integrability, you'll get smooth sample paths. But in general, you can't expect that. And this is the problem. So I just mentioned that discontinuities arise. Where do they arise? Well, it's where you get ties in the distance to the calls. So I have my ambulance base, fixed one up here. Here's the location of that call. If my other base is anywhere on the circle, there's a chance that I'll get these discontinuities. And that is sort of verified if you look at a simple, tiny little simulation with just 2 calls. So I did this. I generated just a couple of calls and I cooked it up. What you're looking at here is a heat plot of the sample path function of the mean response times as a function of the location of the second ambulance. So it's like a control plot, right, but just a heat plot. And you see beautifully these sort of discontinuities on the circles showing up. So this is the kind of sample path function that we're dealing with. Okay, so again, those discontinuities are of order, stochastic order 1/n, and they're becoming dense as n increases in my domain. So I don't know to what extent that's true of all problems, but it's certainly true in this situation. So these are the kinds of optimization problems that I want to solve. And one thing that's kind of interesting is if I just use automatic differentiation to get gradients on my sample path functions, if I have a problem like the news vendor, where everything's nice, it works beautifully and it converges at the rate of stochastic gradient descent that you probably know and love from machine learning. If I try those methods on the bus scheduling problem, those sample gradients are rubbish. And so I'm just not even going to converge, in which case I need to do something else. If I use, this is an interesting thing though, if I use the sample gradients on the ambulance problem with 2 ambulances, where it shouldn't work, it works beautifully. Somehow the sample gradients are aligned with the directions I actually want to move. There's something magical about that problem that makes it work. And I think it's that the sample gradients are not so biased. Those discontinuity effects don't have huge impact on the overall sample path behavior. But I don't know for sure. That's sort of a topic that I'm trying to understand as part of my work. But it does mean that I have to face those kinds of functions. And I have to try to do something. Yeah.
Are the analogical behavior and are those really because of the finite sample and finite sample endpoints, or is there also pathological behavior
in the limit
itself?
Yeah, so great. It's a great question. So I'm kind of conditioning my thinking on having a smooth limit, but then the pathologies, these things come in at finite in sampling. Is it the case that there are problems for which the limiting function itself is ugly? I don't know because I can't compute any damn thing, but I believe there are some problems. Things like if you're dealing with portfolio optimization and you have things like barrier options in those portfolios, barrier options have these discontinuity kind of behaviors, and so you can get things there. But it's actually quite hard to construct examples where the limiting function is ugly. And it's sort of also hard because there are limited analytical results about those guys.
So, and for being nice and the limiting function is just smooth or also something like convex?
I definitely want convex if I can, but if I can't have it, I'll go with smooth. Yeah. You know, there are these beautiful terms like, I'm going to get it right, weakly convex or something functions that are sort of, they have a little bit of negative curvature, but not too much. So you can do things with those functions. So, you know, I'd be happy with just about anything. But you can see that I'm living in the Wild West at the moment. Yeah. Thank you. Yeah. So, so now that we know something about these sample path functions, what can we do in terms of designing algorithms? So I'm looking at the time. So what I'm going to do is just give you a flavor of this. Actually, let me connect it to machine learning a little bit. And I want to point out one more thing that's kind of interesting. And then maybe we'll see how we're doing. Okay. I want to respect your time. So what I've shown you here is very closely related to this gradient estimation technique called infinitesimal perturbation analysis. Doesn't matter if you've never heard of it. It's the same thing as automatic differentiation, basically. So if you use some sort of automatic differentiation technique, which is basically using the chain rule to compute derivatives of your calculated values in your simulation, that's the same thing. Okay, so and if you're not using automatic differentiation and manually coding derivatives, that's also the same thing. If you haven't ever heard of this before, this is just a very straightforward idea. Suppose in your code you write y equals sine x. The compiler sees that and cleverly just figures out that the derivative is cos x. And then if y is then used in a later calculation, you just use the chain rule to update the derivatives as you go. So it's a clever way of doing this. And there are different approaches. There's forward propagation, back propagation, and then there are sort of mixed versions to these things. But fundamentally, they're just derivatives of the code. So we can do that in simulation, and that's called IPA, or infinitesimal perturbation analysis. And back propagation in neural nets that you may have come across, that is the same idea, just organizing the calculation in a certain way. So IPA gradient estimators are unbiased when, in our language, the sample function is nice, and you have some uniform integrability plus one other condition that I won't go into. But that's it. So you, in facing some optimization problem, you should know almost by sight whether you're going to have a good time with the sample path functions or not. And that allows you to choose either a gradient-based descent algorithm or to be wary of using a gradient-based descent algorithm. And so the simulation folklore in our world is, if you detect this problem of discontinuities, don't use sample gradients. And what I'm arguing is that, yeah, you're probably right. But yeah, sometimes use them anyway. You know, the ambulance problem, it seems to have that behavior. I don't know why, but I'd like to know why. And I think it's sort of more, you know, we should use that more often. But when you do run into these problems where you get biased gradient estimators, then hopefully we can appeal to zeroth order kind of algorithms that don't use gradients. One other little tidbit here, you know, just to show you how the connections are present. If you're using some sort of multi-layer neural net, and you have activation functions that are kind of like ReLU, you know, like the piecewise linear curve like this, that's going to have differentiable outputs, and it's going to have nice sample path functions because it's piecewise smooth. You need a bit more regularity than that, but that's just about good enough. If you use indicator functions, you are not going to have nice functions because there's going to be these discontinuities. And so that's going to create the discontinuities in the output. You shouldn't rely on the gradients then. So that's kind of the power of this way of thinking about sample path functions. It applies across disciplinary boundaries. So I was going to show you some of the Lyapunov function analyses here, but I don't think there's much point. Yeah, I will stop. Yeah, so if you want to prove results about convergence and so forth, there are beautiful ways to do that using Lyapunov arguments, and they tie into martingale kind of analyses to get those results. So if you're curious, I'm happy to talk about that. If you're not curious, I completely understand. Thanks for your time today.